I want to welcome you to the webinar on passive solar heating and cooling. This is a webinar about a subject that I've had a passion for my entire career, and it's a real pleasure to share it with you. What I'm going to do is take you on a little bit of a journey of my experience with designing and building and researching passive solar design in buildings over the past 50-some years. And let me see if I can, hold on one second. Oh, there we go. But let's start at the beginning. About 2,500 years ago, this is not a new technology. The technology has made things work better, but in fact, we have known about the concept of designing buildings with the sun for, I don't know, 2,500, 3,000 years. The Greek philosopher Aeschylus, back in 450 BC, he was known as the founder of the Greek tragedy, as well as Socrates. They talked about, only primitives and barbarians lacked the knowledge of houses turned to face the winter sun. So we don't want to be primitives and barbarians. Roman bathhouses were well known for having large south-facing windows to bring the winter sun in to warm the bathhouses. And orientation to the sun has always been a part of Chinese feng shui for thousands of years. We don't even know how many thousands of years. Fast forward to modern times, and we see the first discussion of solar homes back in the 30s and 40s when the architect George Keck designed what he called the House of Tomorrow. Well, this was an all-glass round house, and he was amazed at how warm it got inside on sunny days in the winter before they even installed a furnace. So he went on to start designing houses with lots of south-facing glass. Of course, back at that time, they only had single glass. And his houses were actually sponsored by the glass company PPG. We're all aware of Frank Lloyd Wright's passion for environmental design, and he had a good understanding of designing with the sun. And this is one of the examples where he really went all out on design just for the sun. This is called the Solar Hemicycle house. It was built in 1946. As you can see, it's got lots of thermal mass, lots of south-facing windows, got curtains for drawing at night for insulating the glass. Of course, this is all single glass and not a whole lot of insulation. We've come a long way since this time, and I want to walk you through a process that I started back in the 70s when I joined the National Solar Data Network, where we were monitoring buildings all over the country, and I was actually in charge of the passive solar buildings to develop analytical methodologies, instrumentation, monitoring, and analysis of these buildings. And I attended the first passive solar conference in 1976 put on by ASES. And this was an eye-opener because all of a sudden scientists were talking about the physics and the thermodynamics of passive solar buildings in a way that it actually became a real science. How do you calculate all this stuff? How do you predetermine if these things are going to work? How do we start to refine the materials and the processes that we use so that we can improve the performance of these things? And the whole idea was to design and build a building that needed no heating and cooling system. It would just sit there by itself and stay at a comfortable temperature year-round. So this was my objective. I had the pleasure of and the opportunity to work at the National Solar Data Network, so I got to look at these buildings in a very deep way. We put hundreds of sensors in every one of these buildings and looked at it, the data minute by minute, and developed monthly performance analyses of these buildings. One of the buildings that we looked at, I'm going to show you here in a minute. But let me just cover a few fundamentals before we get into that, just to set the stage for passive solar. Now, I don't know how many of you understand any of the basics or already know all this stuff, but I have to sort of set the stage for it. The first thing is, when you design a building, you want to build the house as energy efficient as possible. When you have a real efficient building with good insulation, it needs very little passive solar to actually run and keep the building at temperature. So building load's the first thing. You want to get that as low as possible. Lots of good technology and information out there about insulation, air tightness, and so on. Orientation's the next big thing. We want to make the major part of the house face south, within 15 degrees or so of south. This includes putting the major living areas on that part of the house and the majority of the windows. And also, when you slope the roof that way, it gives you a good location for your solar photovoltaic panels for the electricity generation. Now, windows are a key part of the passive solar building, and we're going to talk a lot about windows. But basically, you're looking for a low U value. That's the heat transfer coefficient. You want to get that as low as possible. You want to have a high solar heat gain coefficient on the south. That's the amount of energy that comes through the windows in heat. But you want a very low solar heat gain coefficient in the east, west, and north windows, because you don't get that sun in the east, west, and north in the winter. It only comes in the summer, and you don't want it to come in the summer. Thermal mass is another big component I'm going to talk a bunch about. Primarily, we're using masonry. I'll talk about some other techniques we've tried. And it's not only for storing the daytime solar energy so you can heat the building at night, but it also improves comfort. We all know radiant floor heating is probably the most comfortable way to heat the building. But what about if the floors and the walls were all radiantly heated? We have a super, super comfortable house. The next thing, of course, is solar control. A passive solar house can get away from you in the summertime and be unbearable. And so you need to be able to control the sun in the summertime. I'll show you lots of techniques to do that. We also need to control it in the wintertime somewhat, and between day and nighttime. There's also issues with privacy and other things that we'll talk about a little bit. And then finally, passive solar is not just heating, it's also cooling. And so designing the building with ventilation and shade and mass to promote natural cooling is a component we'll talk about a little bit as well. So let's talk about glass, fundamentals of glass, just to put some basics on the table for everybody. So there's about 450 BTUs per hour striking the Earth at any given point in time. And depending on where you are in the world, the time of the day, the day of the year, how many clouds. For instance, if you're in Albuquerque, New Mexico, you're getting twice as much solar radiation striking your glass than you get here in Gaithersburg, Maryland, which was a lesson I learned early on. Also, the angle of incidence, the sun striking the glass, if it's perpendicular to the glass, more sun gets through the glass. The higher the angle of incidence, the more reflection, and therefore the less sun. All of this data on heat transmission is available in both tables and in software. But then going in the other direction is the heat loss, conduction, convection, radiation, and that's generally expressed as a U value, which is the BTUs per hour per square foot per degree temperature differential. We can improve both the solar transmission, expressed as a solar heat gain coefficient, and reduce the heat loss. And this is the dynamic of the technology we've been working on for the past 50-some years. Improve the solar transmission and reduce the heat loss. So we started out with single pane windows, and the main characteristic there was low iron. If you have low iron glass, you get better heat solar transmittance. Then we invented double pane windows, which improved the heat loss value significantly. It cut the heat loss in half, but it also reduced the solar transmission somewhat, because now the sun's got to go through 2 panes of glass. Then we came up with triple pane glass, 3 layers of glass. That did, again, improve the U value, but it reduced the solar heat gain coefficient. So there's a trade-off there. What a lot of people tried to do is add movable insulation to the windows on the inside to insulate it at night. So when you didn't need the sun, you insulate it. And I'll show you some tries at that. We also invented a product called a quad pane window. And this is where we use 2 layers of glass and 2 layers of a very high transparent thin film in the middle. So this didn't reduce the solar heat gain coefficient, but it did improve the U value significantly. We ended up with about an R4, 4.5 insulating value for the window with a transmittance that was very close to a double pane window. Now that was in the market for a little while, but then they invented low E, which is a coating on the glass that rejects heat depending on what side of the glass you're putting it on. And low E is now the technology, state of the art. And then we also realized that the space between the glass, which was filled with air, could be filled with a gas that had a lower conductivity than air. So argon gas, it's a lighter gas, therefore it doesn't transmit the temperature as well as through air. Some people actually tried pulling a vacuum between the 2 layers, and that does work quite well, but it's physically very hard to do. And then the last thing it's really important, I'll talk about in a minute, is thermally improve the frame of the window. Now all this stuff we're talking about is the glass only, but then the glass is in a frame. If you put it in a metal frame, it's not going to work as well as you put it in an insulated frame. So today most windows are manufactured and they mostly use cardinal glass. So one major glass company provides the glass for most of these windows. This is a table from the Cardinal Glass manufacturer's website that shows, and I've got circled here, the U value and the solar heat gain coefficient, as well as other things, for various types of glass that they offer. Circled in red is the clear low E 180, which gives you the best performance we've found for passive solar windows today. Has a solar heat gain coefficient of 64, that's about 64% of the sunlight hitting the glass actually gets through as heat. And an insulating value of 0.26, which is really very good with an argon-filled window. And then for the other sides of the building, the east, west, and north, you want something that has a very low solar heat gain coefficient. So the low E 340 gives you a solar heat gain coefficient of 0.18, which really blocks a lot of the sun heat. But it still has an R value of, or a U value of 0.24, which is actually even better on the insulating side. It's hard to get the high solar heat gain coefficient and the lowest U value, so you try to strike the norm there. But this is what you'll see today. When you buy glass, you want to look at these numbers. You want to specify the actual glass that goes in the window. If you're buying the major manufacturers, you'll be able to specify the exact glass that goes in their window. They offer most of it. So the other thing you want to look at is the frame. Now most windows, all windows, come with a National Fenestration Council sticker on it that's required by code that gives you the U value and the solar heat gain coefficient and the visible transmittance and other things of that window. Now that's the window unit that's been tested, not just the glass. All those values I just gave you were center of glass. So if you look down in the table below, you see we've got metal frame glass, metal frame with thermal break, non-metal frame, and non-metal frame thermally improved. And look at the U values. With a U value of a metal frame window, where your glass is a 0.26, when you put it in a metal frame, the overall window has a U value, 3 times higher, 2 to 3 times higher, because that metal frame is so conductive. But if you get a good non-metal frame thermally improved window, you can get the U value of the entire assembly very close to the center of glass. Important to pay attention to when you're buying windows. Okay, let's fast forward to the future, to the past. And let's start looking at some of these buildings that we were monitoring back in the day. This is one of the, on the left-hand side there, the before, was a building that we monitored in the late 70s, the National Solar Data Network. I had hundreds of sensors throughout this building, monitoring everything about the building to try to understand how it worked. And what we found was in that building that it had way too much sun. Everything was frying in the greenhouse. The plants they put in there died. It overheated like crazy in the summertime. In the wintertime, it was the coldest days, it was wonderful, but the rest of the time, it was unbearable. And so we had an opportunity with this particular builder to take advantage of the data that we collect and say, well, what if we fixed this house? And he agreed to fix the house according to our specifications. And what we did was replace the slope glass, which was the state of the art of the day. If you look at a lot of solar homes back in the early 70s, you'll see that most of them want to have that big slope glass. We replaced it with vertical glass. By the way, this house is in Cincinnati, Ohio, just for reference. It's a pretty cold climate there. We replaced it with vertical glass. And then we monitored that building. Now, the original design had double pane glass with movable insulation called a window quilt. This was a quilted fabric with mylar and stuff that rides on a track and rolls up in the daytime. You roll it down at night, it insulates the windows at night. Well, it worked fine, but it was dependent on owner operation, and it wasn't always done when it needed to be. And we still had lots of overheating because once the sun comes through the glass, pulling down the curtain doesn't keep the heat out, it just blocks the sun. And so that heat built up between the glass and the curtain and came into the building anyway. You have to shade a building on the outside. Shading it on the inside is sort of worthless. The other thing we did was the glass. We were looking at a way to improve the performance of the double pane glass, and we were working with Weather Shield, the manufacturer of the window, and the 3M company, who had this high performance film, and we created this quad pane window. 2 layers of glass on the outside and the inside, and in between was suspended a thin film, which is a very, very high solar transmittance. And so the double pane with the movable curtain had a solar heat gain coefficient, a U value of 0.2 when it was closed. The quad pane window had the same solar heat gain coefficient during the day, but it had a U value of 0.24 all the time. So it actually outperformed with the same glazing area, this sloped glass with a movable insulation. We learned a lot from that. About the same time, the builder was building another house, this time in Syracuse, New York. Now, if anybody knows Syracuse, New York, you know they have very little sun, and it's extremely cold, one of the coldest places in the country. And so designing a passive solar house in Syracuse, New York was a real challenge. And of course, we didn't have a lot of super high performance glass. So we incorporated a system called a bead wall. This was invented by Steve Bear in New Mexico back in the 70s. And basically the bead wall is a layer of glass on each side of a 2x4 frame. And then at night, a vacuum blower fills the cavity between the glass with styrofoam beads and gives you 3.5 inches of styrofoam insulation on that wall. In the morning, the fan comes on, the vacuum comes on, sucks the beads out, and you have double glazed glass. This thing was amazing, and it worked great. For thermal mass in this house, we were experimenting with phase change material. If you look at the picture on the right, there are 4-inch diameter PVC tubes behind glazing that are filled with a eutectic salt. This is a material that melts and freezes at about 80 degrees. And when something changes state between melting and freezing, you get a tremendous amount of heat transfer. Storage capacity gives off that heat when it melts, and it absorbs that heat when it freezes. Very, very efficient, but costly and problematic in a lot of other ways. We've used this in a number of projects back in the day, but it's really not used much today. So here at home, I also was designing houses and additions for folks, and my solutions for my clients tended to be a lot more conservative, if passive solar was actually conservative in the early 70s. This is an addition we did in Annandale, Virginia. It has double pane glass, which is what was available today. We used window quilts on all the windows. We have operable clear stories for ventilating in the summertime, and a little bit of overhang there for shading that top window. The building had a brick veneer, and we made concrete floors and brick floors for the thermal mass. This addition added 30% to the square footage of the house, and at the same time reduced the energy consumption in the house by 30%. So the addition became a major energy feature for the house and reduced their overall energy consumption. And it improved the quality of life of the family because of all the daylight and all that. I spoke to the kids grown up, 30, 40 years later, who grew up in this house, and they said they just absolutely loved living in this environment. Passive solar is an environmental thing. It's not just an energy thing. It's improving the environment of our homes by bringing the sunlight in. Passive solar greenhouses are another component of passive solar heating and cooling. And I don't want to get into passive solar greenhouses by themselves in great length, but let me show you this one because it has a lot of characteristics of good solar design. So the glazing on this is a polycarbonate twin wall, which is commonly used and used today in greenhouses. But this one had a little bit of an active thermal storage system that I've used in many houses since then. If you look over here, this tube is actually a duct, and in there is a blower that blows air, sucks air from the top of the greenhouse. When the air gets hot up there, there's a thermostat that turns on the blower and blows the air into a 2-foot deep gravel bed underneath the concrete slab. And then the air comes out this grill, pushing the wrong buttons. Comes out this grill here and circulates the air through the greenhouse for thermal storage. We monitored this thing, and the rock bed works great as a thermal storage. It's not quite passive. You have to have a motor and a fan, but it does a great job if you can't put all the mass in the building. I had another client that was building a colonial reproduction subdivision here in Maryland, and he wanted to do passive solar, but he said, these are colonial reproductions. I don't want a house that looks like a modern solar house, because the perception was, it had to have sort of a modern look and sloped glass and all this stuff. So I reminded him that right down the road in Mount Vernon, George Washington had an orangery or a greenhouse that he used to grow citrus plants in, trees for his winter crops, and it had south-facing Palladian windows, and it would be a good model for a passive solar colonial home. So we built this. It worked great. The thermal mass was concrete floor with brick, and the wall between the house and the greenhouse was brick, and French doors between the two so you could open and close the space if you needed to. This is an addition in Capitol Hill in DC, owner built. And this was a very low cost project that on a townhouse in Capitol Hill that uses just plain patio doors. The patio doors at the bottom, and then the 4 panels in the middle are replacement patio door windows, and then sliding windows at the top. The homes in DC are all concrete construction, so lots of thermal mass there. Also did some low-income housing rehabs using passive solar design principles. In the early 80s, I joined the National Association Home Builders Research Center and proposed what we called the environmentally responsible house for the 21st century. Well, that name was a mouthful. It got shortened to being called the Green Home. And what was nice about this is I incorporated a greenhouse for the heating, but also for growing food, and also as the gray water beds for water filters for the gray water. It incorporated all the other modern things we see today, including photovoltaics and geothermal and that sort of stuff. But I was trying to introduce passive solar to the mainstream builders of the time, as well as a more comprehensive, integrated, self-sufficient home, if you will. And in the 80s, I also designed and built this house for me and my family in Gaithersburg, 100% solar powered, with batteries, passive solar design. It doesn't look like a solar house. The building on the right is the studio. And this is sort of the southeast corner. This is the studio with the photovoltaics on the roof, a solar thermal system on top of that, and a daylighting system on top of that. So this incorporates a little bit of everything. We've got passive solar, PV, solar thermal, and daylighting in this one building. This building is built out of another thermal mass material called aerated autoclave concrete, which I've built a number of buildings out of. This is mass and insulation at the same time. I'll show you more about that here in a minute. And then the daylighting was from a skylight. Now with a skylight, you want a high visible transmittance, so you have 63% visible transmittance and a solar heat gain coefficient of 0.24, so it doesn't heat up. It gets light in, but it doesn't heat up. And it still has a very low U value. So let's talk about thermal mass, which is the other really important component of a passive solar house. What thermal mass does is it dampens the indoor temperature to where it's almost a constant temperature day after day after day. With a lightweight building, you can see here the temperature tends to track the outdoor temperature, but offset by a few hours. The more you insulate the building and the more mass you put into the building, the more that dampening effect creates almost a straight line here of temperature in the building. Temperature hardly changes. In the summertime it stays cool, and in the wintertime it stays warm, and therefore the heating system and cooling system never comes on. These are the three main systems I use: concrete, poured in place or cast concrete, the aerated autoclave concrete block, and compressed earth bricks, which are my favorites. So I'm going to spend a little time talking about those. And you can see with the compressed earth bricks, we're applying insulation to the outside, which is a critical component to the performance of compressed earth bricks. Just a quick table. You can look at this in a little more detail, but what I want to point out is thermal capacitance of a material in this column. The higher the number, the better. Water is not a very useful means of storing energy in a building, but stone, concrete, and earth bricks have a very high capacitance of storing energy. And then the next number is the thermal conductivity. That is the insulating value. And with a good thermal mass, you want something that has a very low insulating value for the most part, so that the energy can go in and out very easily. So it makes earth bricks a very, very useful thermal mass in the building. It also has a very high density of 1,900 pounds. Concrete's like 2,000. I'm sorry, these are kilograms per cubic meter. But these are the primary thermal mass materials that we're using. In the late 80s and early 90s, I had the opportunity to travel around the world, and I was asked to help the Mandela administration in South Africa rebuild after apartheid. And I saw this as an opportunity for designing in a new way, affordably, and rebuild the building industry in South Africa using the best techniques we knew how to at the time. What I learned was, prior to this point, we had been designing buildings with the metric of reducing energy consumption. Well, these buildings had no energy consumption. They were just darn uncomfortable. They didn't use energy because they didn't have any. So the metric became completely different. So all my modeling tools and design tools were now geared towards modeling and designing for comfort, not for energy. And from that point on, it was a complete paradigm shift in the design of buildings. We're designing it for comfort, not for energy. Because if we can design a building that's comfortable without energy, we've really done the job. And so as a result of that, I developed the Earth Home, which is an affordable, completely self-sufficient house. Heats and cooled by itself with passive solar, natural cooling and heating, earth brick construction made on site. We collect the rainwater for fresh water. Gray water is used to water the gardens. Solar water heater, passive solar water heater, natural ventilation. And we even use a solar oven on the south side for cooking the food. We built a lot of these, thousands of them around the world. And these are some other variations using the same concept, but adjusted to the climate. For instance, in Nigeria, it's a hot mixed climate, hot and humid. And so we had houses that, again, made out of earth bricks to hold the temperature, shaded all the way around. In South Africa, which is a mixed climate, cold and hot, we had north-facing windows, because it's in the southern hemisphere, to collect the passive solar and heat the buildings. In Pakistan, we had both hot and humid climate, so again, building with earth bricks, but with proper shading and so on to maintain comfort year-round. Now, building with earth bricks is like building with any other masonry material. What's nice about it is it can be made on site from dirt. Basically, we're taking dirt, which is clay and sand, and a little bit of Portland cement, putting it in a machine that compresses it at about 1,500 psi. And then we build the wall out of it. We either use a thin set mortar, or these are interlocking tongue and groove bricks that just dry stack. And these are all made on site from the soil on the site. Then we use a concrete bond beam around the top and the corners to strengthen it and provide earthquake resistance and so on. That's then, in this climate anyway, insulated on the outside. In the southern climates and the hot climates, we don't insulate it. It just naturally stays cool with an evaporation effect on the outside of the wall, cooling the wall down. In a cold climate, we have to insulate it on the outside. We used to use rigid foam, but we now use rigid mineral wool insulation, rock salt or something like that, because you get away from the foams. This is a house we built in Falls Church. This was actually featured on House and Garden television. The building is built out of earth bricks we made on site. You can see the machine down there on the left. Insulated on the outside with 4 inches of rigid foam, and then stuccoed over top of that. The only heating system we needed here was pull some heat off the water heater to heat the floors. There is no actual heating system. It's a radiant floor system heated off the water heater. This was featured on House and Garden Television, Renovation Nation. This is Steve Thomas from Renovation Nation. There's an hour-long show. If you see some of the old episodes of that, it was a really well-done show. These are the water tanks, rainwater collection tanks, also part of this build. This is another earth brick construction in Bethesda, Maryland. This is an addition. It went on the back of this normal ranch house. Passive solar design. Completely non-toxic materials. This addition doubled the size of the house and reduced the energy consumption of the house at the same time. This one was outside of the DC area, and This one didn't use the earth bricks. We used a concrete block that was filled, the cells are filled, and then insulated on the outside. And we used an underfloor thermal storage on this one, where we filled the crawl space with gravel, and then you can see a little vent right here at the top of the room here. A fan pulls air from the top and blows it into the crawl space, which is full of gravel, and then it comes out vents in the floor. And that heats the floor. So it keeps the building from overheating on a really sunny day, stores that heat in the floor, and then distributes it as a radiant floor. And it has insulating shades on the windows to shade them, to insulate them at night. This is another small little house we built for a community school, owner-built kind of thing, built out of earth bricks because they were very user-friendly. So the volunteers got together, made the bricks, and made the house. This one uses a greenhouse sun space as its primary heating system, and the walls are compressed earth bricks insulated on the outside. Another compressed earth brick house in Maryland, stuccoed on the outside. You can see the passive solar wall here, and earth brick construction with concrete bond beams for structure. We also did a lot of houses in Mexico. We did a 6,000 home community in Mexico with the earth bricks. Now here they don't need heating. It was mostly a cooling design, but it was like working with adobes, which was the traditional method there. Modern builders all use concrete, and concrete doesn't work as well, and we showed them how to use the adobe made on site. And these buildings have almost no energy consumption. Jefferson, Maryland, up here in Maryland, this building is a 100% solar powered and wind powered and passive solar. That behind the van there is the greenhouse that collects sun. We have about 2 kilowatts of solar, and no, I think it's 3 kilowatts of solar and 3 kilowatts of wind turbine combined to provide the electricity for this house. But what's really unique about this house is it's built with aerated autoclave concrete walls. This is thermal mass and insulation at the same time. So one material gives you about an R21 wall and thermal mass at the same time. Very interesting material. The whole building was built with these blocks and then plastered on either side, and that was it. The sunroom has good glass with low E and high transmittance, has big ventilation windows at the top, awning windows at the top, overhang for shade. In the daytime, the sunroom is open to the living room. At night, it can close up with with sliding panels, glazed panels, to button the house up on a cold winter night. The overhang is designed to completely shade the windows in the summertime, and in the wintertime, the sun comes under the overhang and allows the sun to come in 100%. This is a group of houses called garden atriums. We did down in Poquoson, Virginia. These use glazing on the roof and sloped, which is kind of contrary to everything I've been saying. But what's different about these is that slope glazing has an exterior shading that closes out cuts the sun in the summertime when you don't need it. These buildings are excellent performers, big sun space in the middle. You push a button and the windows are shaded on the outside. And the energy consumption is zero. These are 100% solar powered. You see a few solar panels on the roof of these as well. 100% solar powered community. We've got about a dozen of them down in Virginia. This was the first one with a large atrium in the middle. Up here in Frederick, Maryland. Now, this one's not built out of thermal mass. This one's built with 12-inch thick R50 walls. And when you start building that much insulation into the wall, the building has a thermal mass to it that's a little bit different. And this building is, again, 100% solar, zero energy building. You can see the south-facing windows there on the upper right and the retractable awnings. So when they don't want the sun coming in, the awnings provide the shade. When they do want the sun coming in, they just retract the awning. Very adaptable to whatever weather conditions you have at the time. The fireplace is actually does heat the house also. And you see the operable windows above the doors to allow ventilation, hot air out of the building in the summertime. I've done some commercial buildings. This is Frostburg State University. This is 100% passive solar, heating, natural cooling, photovoltaics, and wind to power this school building at Frostburg State University. The clear stories there, you can see the vents open for summer ventilation when they don't need the heat. Photovoltaics on the roof. There's also a wind turbine. Those clear stories provide both solar heat gain to the inner parts of the building as well as ventilation when you open them. And you can see they have pretty large overhang for summer heat protection. Solar thermal system stores the heat in large tanks, insulated tanks, and then that heat is distributed through the building through a radiant floor system. This is a cross-section where you can see the clear stories that allow the sunlight to come in. This also provides daylight, so you don't need lights on during the day. And it is also designed for daylighting. This is a daylighting analysis showing the illumination of the rooms based on the clear stories, providing the daylight for the various rooms. The blue areas are rooms that don't have the clear stories. So this is actually an off-grid building for Frostburg State University. We used a lot of daylighting in the center sections. You can see the daylighting domes there in the middle. This is what daylights, for instance, the bathrooms. There's no lights on in this picture. That's a light coming through one of those sun tunnels. Cross section of the building, you see the building is made out of concrete. It's a tilt-up concrete construction. So the slabs were poured on the floor slab, then tilted up. Then we added 4 or 5 inches of foam insulation on the outside of that concrete, and then the whole building was stuccoed as the finished. So the whole building is a thermal mass, and very conventional commercial construction techniques. Just show you quickly, this is the backup heating system. It is a wood-fired boiler that heats the building. You load it once a day with logs, and it's a fan-forced, super efficient boiler that heats the building when needed. Building very rarely needs heat, by the way. A couple of more additions. This is a house on a townhouse in DC. We didn't have a lot of solar opportunities, so we created this clear story at the top that lets the sun in. Copper roof. They had an art studio in the back. This one, the clear story, faces north for north light, for the shadows, for lack of shadows for the clear story, for the art studio. One more addition, back of a house in Bethesda. You see it's an all brick house, so we got lots of nice thermal mass to already work with. We added this on the back side of the house, which is mostly windows and super insulated walls. This was the one window on the south side of the house to start with. And we took that wall away and opened it up to the south side, changing the character a little bit to a more modern look. So this is the next to the last house. This is one we did a couple of years ago. This is in Chevy Chase, Maryland, outside of DC, a DC suburb. It's a development from the early 40s. All the houses are very classical design, so we wanted this house to fit in. So that's why it has this sort of Tudor style. We built this house out of structural insulated panels. You're looking at the south side of the house as the front, with all the, that's the window area for the passive solar design, and PV on the roof. The building is made of structural insulated panels, so it's super tight and efficient. You can see in the lower left there the electric system. The gray box on the left is the batteries, lithium-ion batteries, inverter, and the conventional electrical panels. One fun fact is it has a pneumatic elevator. Goes up and down using a vacuum. Kind of fun. These are the insulated panels coming in. We had 6-inch walls and 12-inch roof of extruded polystyrene foam. The whole building went up insulated in just a few days using a crane. Super airtight construction, super insulated, made an excellent passive solar building. Most of the windows on the south side. That's the finished product. This building uses almost no electricity for heating and cooling. So the last building I want to show you is one of the more recent projects we've done. This is a 100% solar-powered, off-grid, passive solar house in Tonytown, Maryland. This is northern Maryland. The walls are made out of poured concrete, 8 inches of poured concrete. We insulated them on the outside with 4 inches of mineral wool, rigid mineral wool insulation, and then stuccoed over top of that. So it's a completely non-toxic wall. The framing was conventional with a non-toxic spray foam insulation in the roof. The floors are concrete with a radiant floor system that's powered by a propane boiler when needed. This building is almost 100% passive solar in that the water heater hardly ever comes on. The backup heating is generally provided by this fireplace, which is an airtight fireplace with outside air for combustion. And then this whole masonry unit has a cavity, and the air that's heated up behind that cavity comes out the top to actually heat the building if needed on a cold winter night. We also have operable skylights, and these windows up here operate so you can get good cross ventilation in the summertime. The woman who lives here has never turned on the air conditioning because the building just stays so comfortable year round. Used a lot of stone on the inside for not thermal mass, but very beautiful too. And you see how thick the walls are. The walls are 8 inches thick with 4 inches of insulation on the outside, so we got a full 12-inch thick wall. And then the photovoltaic system is separated from the house to keep the electromagnetic radiation away from the house, and that little outhouse has the batteries and that in it. It has about a 6.5 kW electric system and a battery system of AGM lead acid batteries that provides 100% of the backup. And then there's a small backup generator for the worst days. I don't think, it rarely comes on. It comes on just to exercise itself, so it stays fresh. So, in summary, let me just walk through real quickly what we've talked about. One, you want to build a very well insulated and airtight house. Orient it towards the south, because that's where the sun is and that's where the heat is in the winter. Masonry walls are preferable, insulated on the outside in a cold climate, and we don't need to insulate them all at all in warm climates. Actually, what happens is the moisture in the building moves through the walls, evaporated on the outside of the wall, and actually provides some evaporative cooling of the wall, which is natural cooling in a warm climate. We generally arrange the main living areas across the south, and now I'm talking about mostly heating climates. The south windows are a high solar heat gain coefficient and a low U value. The rest of the windows are a low solar heat gain coefficient and a low U value. And in the real cold climates, like in Syracuse, New York, and northern parts of the country, window insulation is desirable. There's lots of cellular shades and so on that can be used for that, or just good heavy curtains. You need to shade the south windows in summer. You need to shade on the outside. Inside shade doesn't do anything. You have to shade it on the outside. Movable shades like awnings are the best. Overhangs are good, but the movable awnings are actually better. If you incorporate a sun space, you need to be able to vent it and shade it in the summer. And then you use operable windows or a fan to circulate the air into the house when you need it in the wintertime. We use a lot of sun tubes or skylights in dark spaces, in interior spaces in the building that don't have windows. And these have a high visual transmittance, visual light transmittance, with a low solar heat gain coefficient and a low U value. So they provide the light, but don't provide the heat and don't have the heat loss. And in the summertime, you want to make sure you got good cross ventilation, at least 2 windows in a room. High and low are best to get good airflow through the building. And in all the buildings, we include an indoor-outdoor temperature and humidity monitor. When people pay attention to the temperature outside and the temperature inside, it gives them the ability to, as one of my clients said, sail the house through the climate. So when it starts getting hot outside, you close up the house and wait till the temperature gets lower in the evening, then you can open the house back up and cool it down. And by working the indoor and outdoor temperature and the ventilation of the building, you can literally sail this building through the summer with no cooling and sail it through the winter without any heating. And finally, I'll leave you with one practical thing that I've learned over all the years of working with these things. Simpler is better. Keep the thing as simple as possible. No mechanical systems, no moving parts. The simpler, the better. Well, that's my presentation. I'm happy to open it up now for discussion. We should have some time for some questions.
Yeah, we've got lots of questions that have come in. First one is from Matthew. With the underfloor gravel heat storage, is there a problem with radon gas?
Good question. Radon is a real issue. And in fact, I spent a good part of my career with the National Association of Home Builders Research Center researching and developing radon control techniques. And you have to pay attention to that. Now, what you're doing in a subslab thermal mass is you're pressurizing it. So you're taking house air, blowing it into the floor, and pressurizing it relative to the soil, and then that air comes into the house. Pressurizing the subslab space forces the soil gas away from the house. If you were sucking air out of the crawl space or the gravel, it would pull, it would have a negative pressure to the ground and it would pull the radon in. So you always blow the building air into the gravel to pressurize it to prevent the radon from coming in.
Perfect. And then we've got one from Brian. When you do a rock bin, is there anything special to be done to protect it from becoming a home for rodents and or insects?
Another good question. If it's sealed, you're not going to get rodents. Rodents are not necessarily tunneling under the building and under the footings and going through. The walls are basically concrete, so you're not getting rodents coming through that way. The bottom is generally layers of rigid insulation and polyethylene to prevent dampness and the cold from the ground. I have never experienced insects, although I wouldn't put it past ants and stuff like that to get in there. But rodents, I've never experienced the rodents.
Alrighty. And we've got lots of questions, 10 more. One from Debbie, very interesting homes. Did you monitor temperatures and humidity in the Maryland homes? Wondering about max temps and humidity, say in August. I've found often people's comfort levels are too narrow to forego AC.
Right. And it really is personal choice. The answer is yes, we monitor all our houses, not electronically, but we put monitors in the house so the homeowner can do that. And it really depends on the homeowner. When I first started designing in South Africa, the comfort zone was between 60 degrees and 80 degrees. Now everybody here would say, oh man, 60 is too cold and 80 is too hot. Here, we have like a 2 or 3 band temperature, tolerance that's, in the mid 70s. A little cooler in the summer and a little hotter in the winter, but really tight band because we have thermostats that are, 1 degree variation. And with mechanically conditioned buildings, we're used to that 1 degree variation. You can choose to leave the AC on and the heating on so you can keep that 1 degree variation, but what the house is doing is reducing the amount of time that AC or heating system is going to run. If it starts to overheat, that's why I like the movable insulation. We can shade the windows if we need to. But even with the fixed overhangs, the windows are completely shaded in the summertime, so they're not contributing to the heating. The last house I showed you, the off-grid, the woman who lives there likes the fluctuation in temperature. We went to that house before we put while we were working on it, before we put the air conditioning and heating system in, and it was single digits outside. It was like 5 degrees. It was really cold. And when we got to the house, it was 60 degrees inside. It was sunny the day before. We didn't have any auxiliary heat on, but the house had gone through the night and never got colder than 60 degrees. It's never gotten above 80 degrees inside without any air conditioning. So we can keep a really tight comfort band between 60 and 80. And if you put a sweater on and an extra blanket and willing to live that way, you can get away with no heating and cooling system. But most people have an AC and heating system that then picks up the difference, but it runs very infrequently.
All right. And another question from Evan. In the late 70s, water walls had looked very promising. Is the problem leakage? Could they be put in a floorless greenhouse next to the house so leakage wouldn't matter?
Good question. I did use some water walls. Leakage is always an issue. The other issue is they turn green. Water leaks. You can't get around that. And water walls installed in the 70s have probably all been removed by now because eventually they've leaked. Concrete can't leak. And I like working with materials and techniques that'll last generations and not have a short-term life expectancy. We tried them. They were fun. They look cool, but they're not a long-term solution.
All right. And what do you think about the economics and practicality of hay bale walls?
So, straw bale walls, hay bale, work pretty good in a dry climate. In this climate here, it's too humid for them because they're, organic material, and mold grows and mildew grows on organic material as soon as the relative humidity gets above, 40%, which is pretty low. If it gets to 50%, the growth rate can be extreme. And what we found in straw bale walls is the growth of a black mold, which is highly toxic to humans. So I've never built a straw bale wall in a humid climate. I don't think they're appropriate at all. They're bad health, because you have the potential, you have a real catastrophic failure mode. If any water gets in there, or if the general humidity levels get high enough, you're going to get black mold growing in them, and then the house is toast, and you can't live in it. In a dry climate, an arid climate, where the relative humidity is always very, very low, yeah, it would work great, and I'd use it.
All right. And from Dale, would you still use solar thermal flat plate or evacuated tubes, or only heat pump systems?
So the use of photovoltaics to run a heat pump water heater are actually more cost effective, practical, and reliable than solar thermal hot water heaters. The solar thermal hot water heaters, use them for years and years and years. They work great. They're problematic. They're a mechanical system that can fail. You got nobody to fix it when it fails. And they're really expensive. You compare that to a heat pump water heater, which is an off-the-shelf item, and photovoltaic panels to run that heat pump water heater, or the power from your photovoltaic system that you have powering the whole house, and you have a pretty robust system. So that's the way we go now.
All right. And another question from Don. Any thoughts on a central atrium type high ceiling into a cupola for air exchange?
Yeah, I'm just now finishing a house where we did that. The central stairway ceiling opens up into a cupola that has operable windows on all four sides that are electrically controlled, so we can open and close them as needed for ventilation. And then there's also a ceiling fan up there that can be reversed to literally exhaust air from the house. The thing with natural ventilation is you have to know where your air is coming from. If you pull your ventilation air from a south side asphalt driveway, it's going to be super hot and it's not going to help you one bit. If you pull it from the north side shaded, trellised, or tree shaded area, which is cooler, it's going to help you a lot. So yes, they work great, and I use them often. Most of the time, though, what I'm doing is putting awning windows above the windows so that per the room, you can open the awning windows and ventilate the house, even if it's raining, because you can leave the awning windows open. But it's always good to have high ventilation for exhaust and low air intake on a shaded side of the house.
Great. Okay. And a question from Karen. Our 70s ranch has many passive solar features. Has a vaulted rough cedar ceiling similar to the last home you showed. Unfortunately, we've lost shading from live oaks and now bake in the Florida summer sun. We want to use mineral wool insulation between the roofing and interior wood ceilings. Can it be sandwiched between ceiling boards and plywood for the roofing shingles? What kind of moisture or radiant barrier, and on which side, below or above the rock wool, do you recommend?
So the answer to that is pretty technical, because an unvented roof, which I think is what you're talking about, whether it's a cathedral ceiling and you've got the ceiling on one side of the rafters and the roof on the other side of the rafters, has an issue with condensation, moisture from the house moving up into the ceiling and condensing on the cold sheathing and causing rot. Now, this is Florida, I think she said. I'm not sure of the climate that she's in, but if it's not cooling only climate, and if there's some cold temperatures, you can't just pack the ceiling with a loose insulation, because you'll eventually rot out the ceiling. It has to be vented or filled with, the better thing to do would be fill it with a spray foam. You basically take the ceiling down and spray foam it, and then put the ceiling back, and that'll give you a very robust system. I use a spray foam that has a very low global warming index. It's a water-blown foam called isonine, and Most spray foams have a very high global warming index, like in the thousands, and the Icynene is a water-blown foam, has a global warming index of about 1. And that's all the foam that we use. But
Alrighty.
you have to foam cathedral ceilings in most climates.
Yeah, and Karen, definitely recommend reaching out to John specifically if you have any follow-up questions for that. Another question from an anonymous attendee. Do you recommend slab floors and stay away from like crawl spaces and wood floors?
I love wood floors. I hate crawl spaces. Crawl spaces are problematic for lots and lots of different reasons. You got rodents, you got moisture and mildew and mold, and they're problematic. I prefer slab on grade. You can raise slabs if you need to get up off the ground with a compacted fill. You want to insulate in a cold climate anyway. You want to insulate under the entire slab, not just the perimeter, which is what the code requires. And then it also makes it very easy in a heating climate to incorporate PEX tubing in that floor when you cast it, so then you can use a water heater to provide radiant floor heating. But I prefer a slab, yeah, over a crawl space. Crawl space is sort of a last choice for me.
Gotcha. And from Vincente, for the electrically actuated shades, how long do these last without breaking?
Good question. I can't answer that because I haven't had any break. And I don't know off the top of my head what their warranty is. We use a product that is commercial grade. It mounts on the outside of the window, and it has a shade fabric. You can pick the transparency of the shade fabric, but we usually use something that's got about a 90% shade factor. It rolls up in a cassette and then has tracks down both sides, and it completely covers the windows on the outside. And then when you want to open it, you push a button and it rolls itself back up. The tracks and the shade cloth itself are pretty robust, and I think last many, many, many years. I don't know what the warranty is. The only thing that would fail, I would think, possibly would be the motor, which is relatively easy to replace. But I haven't had to replace any of those.
Awesome. And from Drew Gillette is asking, how many projects or square feet of Southern glass have you done?
Hi, Drew. Good question. I don't know. I mean, I lost count many, many, many years ago, but a lot. All my houses are passive solar in one way or another, and I've been, designing buildings and building them since, a long time ago.
All right. And Roland is asking, do you still do solar hot water?
No. As I said earlier, a heat pump water heater with a photovoltaic panel is actually lower cost and more reliable.
All right, we've got another one from Debbie. How do you feel about LVT luxury vinyl tile, which is so popular nowadays for over concrete slabs, if the surface was not protected during construction to allow for polishing? Do you think that negatively affects the thermal mass substantially?
So, first thing, I avoid vinyl, anything, at all costs. The polyvinyl chloride industry is one of the most polluting industries on the planet, and polyvinyl chloride is not anything you want to have in your home, especially if it's heated. So I don't use vinyl anything. The only concession I have is PVC, CPVC pipe. Sometimes. I usually almost always use PEX piping, which has much less toxins in it. But vinyl is something that you should not use it at all. So don't use it on your floor. It's just a bad product in the world. If you're going to put anything on the floor, use ceramic tile. Ceramic tile is the best of all worlds. It'll last forever, and has good conductivity, looks beautiful. You can put wood floor on top of concrete. It's not a terrible thing. it does affect the, you won't get much heating from the sun from the top, but if you have a radiant floor, you just have to run the temperature of the floor a little bit higher to get the heat through the wood. But you can put wood on slab, on a radiant slab. I typically use tile, ceramic tile.
And then we've got a comparison from Dale Bickenbach. Can you compare your methodology to the current passive house modeling programs, WooFi and PHPP?
Right. So it reminds me of back in the day, we used to have two camps. We had the solar camps, and they all belonged to ASES. And then we had the super insulation camp. And the super insulation camp just said tiny windows and lots of insulation, and then you don't have any utility bills. And the solar camp said, well, if you just put lots of windows in, that'll heat the house, and that's fun too. Well, the two have sort of come together, and we do the best of both worlds now. Passive house is more of the super insulation camp. We don't have a strong passive solar lobby anymore. We used to have a passive solar industries council, but that doesn't exist anymore. But in my mind, personally, most of the cost-benefit analysis I've done on passive house requirements, at least in this climate, were not cost-effective. I can get the building to net zero, which was always my goal, at much lower insulation levels than passive house would require. Basically, I'm doing thermodynamic modeling of the house and energy modeling, and I do parametric analysis on the various components to come up with the optimum mix for cost and performance. And my end goal is to get a net zero house that uses no fossil fuels. And if I can do that, that's where I stop. I don't go beyond that. In this climate, in the Washington metro area here, mid-Atlantic, you know, I stop at about an R28 wall and an R50 ceiling, which is just a little bit better than code. And I do full under slab insulation with 2 inches of rigid R10. And the windows, I showed you the specs on the windows that I use. But I don't go to a full passive house spec. Even though we're passive house certified and all that, it's usually it's not cost effective.
Okay. And a really good question from Debbie Coleman. Will you be having any of your homes on the National Solar Tour this year?
I think we're going to have that last one I showed you on the Solar Home Tour. Many of them I've shown you were on the Solar Home Tour at various times of the year, including this one, my own house. We had it on the tour for years. But I'm working with the homeowner. I think she's going to agree, and we'll get that one on the tour this year. That's the off-grid house, the last one I showed you.
Yeah, that's awesome. That would be so great, John. And I just want to send you a couple of hellos and wonderful presentation comments from a couple of our attendees. Drew Gillette says it's great
Drew.
to see you.
Voice from the past, wow.
And who else do we have here? We've got Drew that says nice Xmas tree, Christmas tree. And Brian Schuneman, excellent presentation, great information, well laid out. Really appreciate you sharing your expertise in such a clear and understandable way. And hello from Hap Haven. Hi, John. Great to see you and your work. I think we met at the second National Passive Solar Conference in Philadelphia in 1979.
Good grief. Hey, Hap.
Yeah, so that's awesome. And we've gone through all the questions and comments, and Carl asked, can we watch this again? That is a yes, Carl. This has been recorded, and I will send you all the YouTube link once I have it up and live later this week. So thank you so much, John.
My contact information, my email's at the bottom of the page here, and my website, so feel free to contact us and or me, and we can continue the conversation.
Perfect. Thank you. Thank you so much, John. We really appreciate your expertise on this webinar in sustainable design. It's always such a pleasure to work with you. And thank you so much to all of our attendees. Appreciate your attendance and participation today.
Thank you.
Thanks, John. Have a great day, everyone.